Good morning, students. So today we are going to discuss about the topic principle of superposition. Right. So in the last classes we know how to calculate the stress strain, for a single member or a composite members, how to calculate stress and strain. Here the principle of superposition will be useful when you have a member. So for example, if you have a member like this, a rod or a bar, so it is acted upon by different forces. Let us say I have force here, P1 force, here it is P2 force, here it is P3 force, here it is P4 force. So there are different forces which are acting internally, so at intermediate points of the bar, along its length, at intermediate points different forces are acting. So these kind of members, can be analyzed by using principle of superposition. See what it means, that the total strain caused in this member due to these P1, P2, P3 forces can be written as algebraic sum of strains caused in individual member. See, in this bar we can divide this total bar into different sections. Here up to here one section, up to here one section, up to here another section. There are three sections. So the total strain, in order to calculate the total strain caused in this bar, what you can do is you can calculate strain in first bar, strain in second bar, and strain in third bar, and you can add the total strain. So this is nothing but principle of superpositions. It means that we are superposing individual quantities to get the resultant value, overall. So if I represent the total strain is capital delta in that member, so the equal to delta 1 plus delta 2 plus delta 3, individual strains in each member. Now what is the strain formula? So strain can be written as, for example, if there is a bar here, small bar I have taken, so I have applied a load P here, another P is here, under equilibrium within elastic limit. The strain caused due to this P load can be written as PL by AE. So this is not PL by AE, it is P by AE. P by A, right? So strain is nothing but delta L by L. You can write down strain as delta L by L equal to P by AE. So you can write down delta L equal to PL by AE. This is the change in length in a bar subjected to a tensile load P. That change in length, let us see, it is changed to here. So this is delta L. Now if you observe in this bar, there are three sections, right? So the total change in length in the bar can be taken as change in length in bar 1 plus change in length in bar 2 plus change in length in bar 3. So what I can do by using principle of superposition, total change in length equal to change in length in bar 1 plus change in length in bar 2 plus change in length in bar 3. Okay, so you can write down like this, total change in length, or you can also use strains, total strain equal to strain in bar 1 plus strain in bar 2 plus strain in bar 3. Okay, this is also can be written, or you can take it as a total change in length depending upon how it is asked. Okay, now let us see how to solve these kind of problems. Let us take one problem, example problem. So there is a bar is there. Okay, so there are different forces are acting on this bar. One is 8 kilonewtons, another is 4 kilonewtons, another is 2 kilonewtons, another is another 2 kilonewtons, another is 4 kilonewtons. So around kilonewtons, these are also kilonewtons. So now these are the forces which are acting internally along the bar. Now you divide this bar into different sections. So up to here I will take one section, up to here another section, up to here another section, up to here another section. So let's give name A, B, C, D, E. Okay, so let us say the length of the section 1 is L1, L2, L3. So I am just mentioning here it is Ln. Similarly, there are different sections. You can have in between also, you can have different internal loads are applied. You can have different sections you can divide. So that's why I'm taking Ln, the last one. Now we need to analyze this kind of system. Now what you do is, first you decide how many sections this bar has. This bar has 1, 2, 3, 4 sections, right? So total sections it is 1, 2, 3, 4. So the first step in solving this kind of problem is you draw the free body diagram of each section. So let us take free body diagram of section 1. Okay, so I'm taking section 1 free body diagram. This is the free body diagram of section 1. Okay, so here this bar is under equilibrium, right? So under the application of these forces, this bar is under static equilibrium. So it means that there is a force 8 kilonewtons which is acting on the left side of this section 1. So same force would have been applied this side. The same force will be there. So this is 8 kilonewtons. So just write down the same force, because this is already, you know, because 8 kilonewtons it is applied at one end. So other end also it should be 8 kilonewtons, it should be there. Otherwise it will not be under equilibrium. It will be under continuous deformation, right? But it is slowly deforming. So at any instant you can take this bar is under static equilibrium. At that instant the load applied at this section at B will be the same load as 8 kilonewtons. So this is 8 kilonewtons. This I have mentioned. Okay, but 4 is also there. We'll see later. So how we can accommodate this 4 kilonewton load also. Now this is the first section. So next what you do is, next go to free body diagram of section 4. Section 4. So I'm drawing the section 4. This is section 4, and there is a 4 kilonewtons load is applied at right hand side. So in order to keep this under equilibrium, this same quantity of force will be there. The same quantity of resisting force will be there the other side, that is 4 kilonewtons. Okay, so now what you do is, see here we have added 8 kilonewtons, here you have added 4 kilonewtons, right? Now take the section 2, free body diagram of section 2. Now in section 2 we already have 4 kilonewtons, right? So section 2 I am drawing. This is already there, right? The other side it is 2 kilonewtons. The other side is a 2 kilonewtons, right? Now here we have mentioned 8 kilonewtons, right? So what you do is, there is a simple logic here. See, at this point you just add 8 kilonewtons this side and 8 kilonewtons this side, 8 kilonewtons this side and 8 kilonewtons this side, because by adding these two opposite forces it will not change the motion of the body, it will not change the physics of the problem, because these two will get cancelled each other, right? So I am just adding 8 kilonewtons this side and 8 kilonewtons this side at some point, the same point where this section is there. Okay, now this 8 kilonewtons already you have mentioned in this. Okay, now the other 8 kilonewtons you mention here. Other 8 kilonewtons you mention. Then what is the total load here which is acting? It is 8 minus 4. So the resultant force is will be 8 minus 4, this is 4 kilonewtons, right? So that will be the resultant force at that point. So the same force will be applied at the other side also, right? The same 4 kilonewtons will be there the other side also. So now what you do is, you apply the same 4 kilonewtons force the other side. So this is section 2. So there should be 4 kilonewtons force at section C. Okay, section C, there should be 4 kilonewtons Newton load should be applied. Then only it will be under equilibrium. Now I am redrawing the section 2. This is 4 kilonewtons. Section C, section B, this is also 4 kilonewtons. Right? Now go to the another section. Section 3. Free body diagram. Now there is a 4 kilonewtons load you have mentioned here. So what you do is, again go to this diagram. Now at section C you add 4, you subtract 4. Okay, so it will not change the physics of the problem. So you are just adding 4 kilonewton load and you are subtracting. So both are away from each other at one point. So it will not change the physics of the problem. Now this 4 kilonewton force is already this force which is pointing towards right side, it is already mentioned here. Okay, so the remaining, when you are drawing free body diagram, the remaining forces will be, this is 4 kilonewtons and this is 2 kilonewtons. So when you are drawing free body diagram, so there is a 4 kilonewtons and there is a 2 kilonewtons, right? And we'll see later what here it is. So here the resultant will be 4 minus 2, 2 kilonewtons. So the resultant force will be 2 kilonewtons at point C. So in order to keep this under equilibrium, the same 2 kilonewton force would be there the other side. Okay, the same 2 kilonewton force will be there other side. Now if you go to section 4 free body diagram, already I have drawn, but if you go to section 4, so this is 2 kilonewtons you have applied. Now you just add 2 kilonewtons this side, 2 kilonewtons this side, subtract and add 2 kilonewtons at one point, right? Now this 2 kilonewtons is already mentioned, so there will be this 2 kilonewton force and this 2 kilonewton force will be there. So here 2 kilonewtons force, another 2 kilonewton force will be there. So at this section you already know it is 4 kilonewton force. It is D. Now the resultant force will be 2 plus 2, 4. Now the free body diagram will be at section E and section D. This is 4 kilonewton and this is 4 kilonewton. This is section 4. Okay, so now this is the way you have to draw the free body diagram for all the sections. Now when you combine section 1 to section 2, so there is a 4 kilonewtons this side and there is a 8 kilonewton this side. When you have combined, 8 minus 4 will become 4, so you will get the resultant 4. Similarly, when you have combined section 2 and 3, so there is a section 2 here, the section 2 is, this side is 4 kilonewtons, section 3, this side is 2 kilonewtons, so 4 minus 2 will be 2, so the 2 will be there, Similarly, when you combine 3 and 4, section 3 and section 4, so here it is 2 kilonewtons this side, right, this side 2 kilonewtons. So and sorry, here if you see this side it is 2 kilonewtons at D section, it is 4, so 4 minus 2 it will be 2, resultant 2 will be here. Okay, so when you combine all these sections you will get the actual member, the given member. You should get this given member. Okay, so you have to make sure that, otherwise your calculations will be wrong. Now after drawing the free body diagram, so what you do is, if you want to find out the total strain, so let us calculate individual strain in section 1 equal to PL1 by AE. So A is nothing but cross section area of the section 1. If section 1 area is different, you can mention this is A1 E1 of length L1, so it will be A1 E1 L1. P will be the load which is acting. This is 8 kilonewtons and this is also 8 kilonewtons, so it will be 8 L1 by A1 E1. Okay, so this is the actually it is a change in length, you can say change in length in section 1. Okay, so when you are calling strain, then you should not keep this L1. So the change in length in section 1 is PL1 by A1 E1. Similarly, change in length in section 2. In section 2 will be, so what is the free body diagram of section 2? Go back to section 2. Section 2 free body diagram is this one. 4, let us say the length is L2 is given, area is L2 and Young's modulus is E2. So then it will become 4 L2 by A2 E2. Similarly, change in length in section 3 equal to, we go to section 3. Section 3 is 2 kilonewtons force which is applied. So it is 2L3 by A3 E3. Okay. Similarly, change in length in section 4 will be equal to 4ln by an 4ln by an. So that is the change in length in section 4. See, so this is the individual change in length of each sections. Now if you want the total change in length, you can add according to principle of superposition. This is according to principle of superposition, and this principle of superposition is true only when we have a very small strains. See, because our strain is very small, it is in mm, 1 mm, or it is less than 1 mm or less than 2 mm. So you can apply this principle of superposition for smaller strains. For larger strains you cannot apply. So the total change in length will be 8L1 by A1 E1 plus 4L2 by A2 E2 plus 2L3 by A3 E3 plus 4L1 by AN E. So this is how you can find out the total change in length, okay, in that member. If they ask you about the strains, total strain, so you can add strain. If they ask you to find out the total strain, the strain in each member, delta 1 plus delta 2 plus delta 3. This is the total strains. It is represented with delta. Okay, so like that you can just add any number of members, right? So the important thing here is you should know how to draw the free body diagram of the each member. Okay, each member of that total bar. Okay, the total bar you have to divide, and each bar you have to draw the free body diagram. You should know how to draw the free body diagram, right? Now, so we'll see how to draw the free body diagram. One more problem. So let us take one more problem here. There is a bar of varying cross section. Here this is A, this is B, this is C, this is D, and here it is 8 kilonewtons applied, and this is 2 kilonewtons applied, and this is 4 kilonewtons applied, and this is 10 kilonewtons applied. Right? Now you have to draw the free body diagram. This is area A1, A2, and this is A3, L1, L2, L3, and this is E1, E2, E3. These are the Young's modulus. Now, before drawing the free body diagram, what you do is you take a pencil. Here there is 8 kilonewtons applied, right? So you take this point. At this point, so if you draw the free body diagram of AB alone, then this side will be 8 kilonewtons, that side will be 8 kilonewtons. So how you will get 8 kilonewtons? So what you do is you just add 8 kilonewtons here and subtract 8 kilonewtons here. By using pencil, you just draw it. Okay, 8 kilonewtons this side, 8 kilonewtons this side. Now here there is a 10 kilonewtons this side. So obviously this side will be 10 kilonewtons will be there when you draw individually for third section. So what you do is you just add 10 kilonewtons this side and subtract 10 kilonewtons this side. So draw with a pencil. Now go to the free body diagram. Free body diagram of section 1. Right, section 1 if you draw, I'm just drawing section 1. Now here if you see, in order to keep this under equilibrium, this side is 8 kilonewtons, it is already given. So this side also it should be 8 kilonewtons. right? So this load is already applied. What about the this load is already applied, right? So now you what you do is you just strike off this load after applying. Strike off this load. Now go to section 3. Always try to draw the free body diagram first, two extreme sections, this section first time and last section second time. Okay, so it will be easy further if you draw free body diagram for the middle sections. So you take the third section. So this side is 10 kilonewtons, so this side also 10 kilonewtons should be applied. It should be 10 kilonewtons internal resistance force, then only this member will be under equilibrium. So this 10 is already over, you applied. Now come back to section 2. So this is section 2. Okay, section 2, if you take, now the remaining forces are, so if you take the middle section, what are the forces left? This is 8 and this is 2, so 8 minus 2 is 6. So here it is a 6 kilonewtons, and here also if you see, this is 10 and this is 4, 10 minus 4, 6 kilonewtons. So this is for section 2, section 3 and section 1, right? So this is how you can draw the free body diagram. So after that you can calculate whatever you want to calculate. So this is very simple, right? If you combine these three sections, section 1 plus section 2 plus section 3, you will get this total, the given problem. Okay, 8 kilonewtons, 2 kilonewtons, 4 kilonewtons, 10 kilonewtons. Okay, but this is important, how much you are adding, how much you are subtracting based upon the extreme load. You have to add and subtract. See here what we are doing is we are calculating what are the internal forces. These are the internal, one side is external force, another side is internal force, right? So the internal force also should be the same as that of external force, right? So accordingly you have to add and subtract here. Okay. Then you will get the total.